Corsey here. Now I'll be going over the solutions to the 2022 paper in some detail. So since this is a fairly long video, I've created headings for each question in the timeline below the video so that you can easily find the particular solution you're interested in. You should see the question numbers as you slide along the timeline. So let's begin the solutions. So here's question 1, and we're asked to determine the equation of the line that's perpendicular to the line with this equation. And we're told it passes through the point -1, 6. Now, just before we get into this, just a reminder, if we're trying to find the equation of a line, there's two things that we should know. First one is a point on the line, and let's suppose its coordinates are A and B. And we also need to know the gradient of the line, and let's suppose that gradient is M. Then the equation of that line is y minus the y coordinate, that's y minus b, equals the gradient times x minus the x coordinate. So it's y minus b equals m times x minus a. So that's the formula for the equation of a line. Do we know a point on the line? Well, yes, we're told -1, 6. Do we know the gradient of the line? No, but we know it's perpendicular to this line. So let's start out with 5x plus 2y equals 7 and attempt to find, first of all, the gradient of this line. Then we can deal with the gradient of a line perpendicular to that. Now, we're going to use the fact that another form of the equation of the line, y equals mx plus c, and we know that this gives you the gradient, this coefficient of x, the number in front of x. So let's transform this into this form. So let's take 5x from both sides. Now take away 5x. We've still got that 7. And let's divide both sides by 2. So we'll divide each term here by 2. So it's -5x over 2. That can be written as, see, there you go, that's a -5x over 2. Another way of writing that is -5 over 2 lots of x. These are exactly the same. Plus, and we have to divide the 7 by 2. Now, it would appear, therefore, that the gradient is -5 over 2. Now, if we know that, then we can work out the gradient of the line perpendicular to that. So remember, there's the result that says the gradient of a line times the gradient of a line perpendicular to that must come to -1. So for instance, 2 and -1/2. A line has gradient 2, perpendicular line would have gradient -1/2. If we've got a over b for the gradient, then remember we invert that fraction and change the sign. And if you multiply these two together, the a's cancel, the b's cancel, and we get a -1. So we invert and change the sign. So that would imply that the gradient of a perpendicular line would be 2/5. We've inverted it and we change the sign from negative to positive. So I think we've got the two facts we need. So the gradient is 2/5, and the point on a line, well, we were told that in the question, it's -1, 6. So we're sitting looking at this information, that's your -1, 6, and the gradient here, 2/5. So we can use this formula. So the equation required equation is y minus the y coordinate, that's y minus that 6, y minus b, equals the gradient m, which is 2/5, times x minus the x coordinate, which is -1. That's x minus a. So take away -1, that'll be adding 1. Now let's tidy this up. Multiply everything by 5, both sides by 5 to get rid of this divide by 5 here. We'll get 5y minus 30. Multiplying this side by 5, we'll get rid of that divide by 5, and we're left with a 2 outside this bracket, which we can then multiply out. So we'll get 2x plus 2. And let's just get these constants together. So we've got 5y equals 2x, and we're adding 30 to both sides, so we get 32. And there it is. That's one perfectly valid form for that. There's others. You could have written 5y minus 2x equals 32. But it's polite to get rid of fractions in your final answer when you're giving an equation. Get rid of the fractions and it looks nicer. So here's question 2. We have to evaluate this log expression. Now, the laws of logs, one of the laws of logs deals with numbers at the front of log expressions. And it's the one that says that n times log to the base b of a, then this n can drift up and become a power. There we go. So n lots of log to the base b of a is the same as log to the base b of a to the power n. That number at the front has drifted up to the power. So in this case we would get log to the base 3 of 6, and that 2 drifts up there to become a power minus this. Another way of looking at that, if we look at for instance 2x is x plus x. In the same way, 2 lots of log to the base 3 of 6 would be log to the base 3 of 6 plus log to the base 3 of 6. That's what 2 times an expression means. You've got expression plus itself. And if we're adding logs, well, there's another law of logs. If you're adding 2 logs, then you're multiplying these numbers. So that's another law of logs. Add the logs, you multiply the numbers. And therefore in this case, if you're adding these 2 logs, then you'll end up multiplying these 2 6's together. And that's 6 squared, which is what we have down here. So we've got log to the base 3 of 6 squared, that's 36. And we're subtracting log to the base 3 of 4. Another law of logs that's very similar to this one here. If you're subtracting 2 logs with the same base, remember it's always to be the same base or these laws wouldn't work, then you're dividing the 2 numbers. So add 2 logs, multiply the 2 numbers, subtract 2 logs, you're dividing the 2 numbers. So in this case we've got log to the base 3 of 36 divided by 4. Now 4 goes into 36 9 times, so we're ending up with a log to the base 3 of 9. And yet again, here's a result that you should know. Let's do a few examples. Log to the base 10 of 100 is 2. Why is that? Because 100 is 10 squared. There's a log up there. What power do you raise 10 to get 100? The answer is 2. That's one way of reading this. And log to the base 10 of 1000, likewise, would be 3. Why is that? Because 1000 can be written as 10 cubed. What power do you raise 10 to get 1000? Log to the base 2 of 8. Well, that's also 3. What power do you raise 2 to get 8? The answer's 3. 8 is 2 to the power 3. And here's a harder one, but log to the base 2 of the square root of 2. What power do you raise 2 to get the square root of 2? Well, think about it. That's a half. Why is that? Because the square root of 2 can be written as 2 to the power half, and so it goes on. So we can read this as, what power do you raise 3 to get 9? And the answer's 2. And you say, well, why is that? Because 9 is 3 to the power 2. 9 equals 3 squared. So the answer is 2. Yeah, that's possibly not the only way we can do this. There's a wee bonus solution here, not one that possibly you would have thought of, but we can break down that 6 into a 2 times a 3. And we can rewrite the 4 as 2 times 2. That's a 2 squared. Now, remember this law over here. Adding logs multiply the numbers. Here we are multiplying the numbers, so we'd be adding the logs of 2 and 3. But remember, it's double that expression, so you'd have to double the whole of this expression. So we'd have twice this and twice this. Minus, and here's this law where the number at the front drifts up as a power, or the power can drift down and become a number at the front. So this would be 2 lots of log to the base 3 of 2. Now, it might not seem we're getting very far here, but gosh, look, 2 lots of log to the base 3 of 2 minus 2 lots of log to the base 3 of 2. Well, these cancel. And we're left with 2 times, oh, and look, there's a log to the base 3 of 3. So that's this type of thinking that we're involved in, which is, what power do you raise 3 to get 3? And the answer there is 1. Well, why is that? Let's think about that. Log to the base 3 of 3 is 1, because you can write 3 as 3 to the power 1. And we end up with 2 as before. So that's an alternative way of doing that. Log questions are often like that when you're simplifying log expressions. There's 2 ways of going about it. You either make larger and larger numbers, or you split the numbers down into factors and work away with the expressions that you get. Here's question 3. We're given a function h with its associated formula, and we're asked to find the inverse function. Now, writing down h of x equals 4 plus a third x, that tells you what happens to x when you put it into the function h. Out comes 4 plus a third x. Now, the inverse process takes this in reverse. It's called h to the minus 1, the inverse process. If we put y in, what do we do to y to get x again? Now, the clue here is to say, well, look, we've got y equals 4 plus a third x, a formula where we know what to do with x to get y. That's y over here. We know what to do with x to get y, but we don't know what to do with y, with this, to get back to x. So we have to change the subject of this formula and get x on its own. So let's try and do that. First of all, I'm going to take 4 from both sides. And then since it's x I want to get on its own, I want to get rid of this divide by 3. So I'll multiply both sides by 3. So this right-hand side gets multiplied by 3, and we get 1x. 3 lots of a third is 1x on the right. Let's write it the normal way for a formula. X equals 3 lots of y minus 4. So what we're saying here is that if we put y in, we should get x back out. This tells us that x is 3 lots of y minus 4. So let's try it with a number. 3 would work. Nice easy number. So if we put 3 in, each function h tells us we do 4 plus a third of 3. Now a third of 3 is 1. 4 plus 1 is 5. So presumably if I put 5 into the inverse function and do all this to it, I should get 3 back. So let's put 5 into this. We do the brackets first. 5 minus 4 is 1. 3 lots of 1 is certainly 3. So that works. 3 in, 5 out. In the inverse function, 5 goes in and 3 is returned back out. X goes in, y comes out, y goes in, x comes in, out. There's a formula, x and y, where y is the subject. We've changed the subject. We have a different formula where this time x is the subject. Now what we'd like to do now is we normally give descriptions of functions by putting x in. In this case we'd put y in, and this is what we do to y. So if we put x in, this is what we'd do to x. We'd get 3 lots of x minus 4. So we're just swapping the roles of x and y around here, because normally we give descriptions of functions with an x. So h to the minus 1 of x, the inverse function, has this as its formula. Differentiation question, where we've got a fairly complicated looking expression here which we're asked to differentiate. So the rules of differentiation, the main one is that if we have x raised to power n, for instance, then we can differentiate that and get dy by dx by bringing the power down to the front and taking 1 away from that power. Now, it doesn't matter if there's a number multiplying this. If it was double that expression, that answer would just be double what we had. So it would be a times this. There'd be an a times in there. Sorry, a n minus 1. So multiplying by a number, you just multiply your answer by the same number. So that would take care of this. It does not take care of this because that's not written as a power of x. So we have to know one other thing about powers, and that's if we have a fractional power, then this tells you the power, this tells you the root. I sometimes think of x to the power 3. It's the Irish power, x to the power 3. And we've got the power comes in from the sunlight at the top through the leaves. That's how the tree gets its power. So the power comes in at the top, and all the nutrients and so on come through the roots at the bottom. So power at the top, roots at the bottom. That's the Irish power. But x to the power m over n would therefore mean that we've got the nth root x to the power m. Now that's bang on this one. If we compare that with the square root of x cubed. Now square root means it's a 2. Square root, cube root's a 3, fourth root's a 4 there. So we've got power 3 root 2. So power 3 root 2. X cubed and the square root. Doesn't matter whether it's the square root of x cubed or x, the square root of x cubed. Both of these are the same. But in this case, they're cubing x and square rooting. X to the 3 over 2. So let's first of all rewrite this. We'll write the question down again. There it is. So the rewriting, we're preparing for differentiation. So this one, power 3 root square root. So it's root 2. So 3 over 2 is the power. And this second expression is ready for differentiating. So we're now prepared for our differentiation, so we can go ahead with that. So it therefore means that dy by dx will be, and we use this rule, bring the power down to the front, 3 over 2, times x, take 1 away from 3 over 2. Now 3 halves, take away 2 halves, will give you 1 half. So we'll get 1 half for the power. This rule, -1 comes down to the front. It just multiplies this -2 that appears there. -1 times the -2 is +2. And take 1 from the power. That's not 0, that's -2. Remember, if you subtract, if you're in the number line at -1 and you take 1 away, you've reached -2. You don't go and add 1, which would give you 0. So take 1 away from -1, you get -2. So there we are. We've differentiated it. And that would be an acceptable answer. That would give you your full marks. Question 5. We're given a line and it makes an angle of pi upon 3 radians with the y-axis. That's slightly unusual. We're usually told it's angle with the x-axis and passes through the point -2, 0, as shown below. Determine the equation of the line. So, equation of lines can be got by knowing a point on the line. Suppose that's AB, and if we know the gradient was m, then the equation is y minus b equals m x minus a. That's the well-known formula for that. So, do we have a point on the line? Yes, we do. -2, 0 is on the line. Do we have its gradient? No, we don't. But we do know the angle it makes with the y-axis. Now, angles and straight lines. If a line makes an angle theta with the x-axis, then its gradient is tan theta. That's because, remember, we make up a wee right angle triangle. Tan is opposite over adjacent. That's the y over the x. Distance up divided by distance along, or rise over run, or however you know, or however you've been taught about gradients. Opposite over adjacent will give you the gradient. So it's the tan of the angle that this makes with a line parallel to the x-axis. It's this angle in here. Now we know this makes a right angle with the y-axis, so we're basically to take pi upon 3 away from pi upon 2. And that's your right angle, and we have to subtract pi upon 3 from that. So we think 6ths of pi. This one is 3 lots of pi upon 6, and this one is 2 lots of pi upon 6. So 3 of them, take away 2 of them, we'll get 1 of them, pi upon 6. You might like to think in terms of degrees. You know this is 60 degrees, or you should. and we take 60 from 90, we get 30. So this is 30 degrees, which is pi upon 6. So that's it worked in radians, but you can convert if it's easier for you. So that angle in there, pi upon 6. So the gradient of this line, gradient of line, will be the tan of pi upon 6. Now, pi upon 6, 30 degrees, that comes about, we can work out exact values if we have a equilateral triangle and chop it in half. Now, if we start out with an equilateral triangle of side, all the sides are 2, chopping it in half, this side would have a 1. This angle in here would be half of the, there's 360 degree angles in there. This would be our 30, or pi upon 6 radians in there. And tan of pi upon 6 would be the opposite, 1 over this side here. Now that's one of the small sides in this right angle triangle, where the other small side's 1 and the hypotenuse is 2. So 2 squared is 4, minus 1 squared is 1, that gives us 3. So it's the square root of 3 this side. So the tan of pi upon 6, or 30 degrees, is opposite over adjacent, 1 over root 3. So that's the exact value, tan pi upon 6. So that's the gradient of the line. We do know a point on the line. That's -2, 0. So we have everything we need to use this formula, y minus b equals mx minus a. So let's do that. So the equation is y minus b, that's just a 0, equals, y minus 0 is just y, the gradient, x minus -2, that's plus 2. And some people like to tidy up. I think that would probably give you your full marks, but let's multiply through by root 3. So root 3y, that gets rid of this fraction. We could just get a 1, the root 3 vanishes, and 1 times x plus 2 is x plus 2. And there's a healthy equation without fractions. Now there are other ways of doing that. We could have used y equals mx plus c, and we could have plugged in the 1 upon root 3 and then determined c by using the point -2, 0. X is -2, y is 0. So we get 1 over root 3 times -2 plus c. And that would give us a value for c. If I add 2 over root 3 to both sides, c would be equal to 2 over root 3. And there I would get the same formula, maybe not obvious, but y equals 1 over root 3 x plus 2 over root 3. And if I multiply both sides by root 3, I've got root 3y equals x plus 2, which is what I've got in this case. So that's an alternative where you substitute in the coordinate values into y equals mx plus c. So here's question 6, a good old definite integral, where we have to integrate this expression and plug in values. So let's remind ourselves of the rules for integrating. I mean, the very basic rule when we integrate x to a power, what do? We increase the power by 1, and then we divide by that new power. And remember, if you're integrating, there's a plus c. In this case, there won't be a constant of integration because we're plugging numbers in. We would expect a number at the end for our answer. So that's what happens. However, we're not integrating x to a power here. We're integrating a linear expression to the power n. linear expression being 10 minus 3x. So it's got an x term and a constant. So it's different from a simple x to a power. But the same basic rule goes on, that this linear expression to power n, we will increase the power by 1 and divide by that power. So that's exactly what went on up here. However, because it's a linear expression, let's put a linear, we'll have a x term and a constant ax plus b in there, and the wee adjustment that we have to make when it's ax plus b is we look at the coefficient of x, that's a, we divide by it. So it appears in the bottom of this fraction multiplying that n plus 1 that's there, that new, dividing by the new power. So that's the rule, and that's the rule we're going to have to use in this case. So we go ahead with this integration. We take that linear expression, we raise this power by 1, so we've got a negative a half plus 1, that's negative 1 half plus 2 halves, that's just 1 half. So adding 1 to negative a half will give us positive a half. So we increase the power by 1 and divide by the new power. We look at the linear expression, and in particular we look at the coefficient of x, the number multiplying x, and that'll include the negative. So it's negative 3, that's what appears down in the bottom of the fraction, and if there's something else sitting there, we just multiply the two of them together. So we've got a negative 3 times that half. Now, because it's a definite integral, let's put square brackets round, which just basically mean once I've sorted this mess out, I'm going to plug the value 2 in, and I'm going to plug the value negative 5 in, and see what we get. So we have a case of tidying up what's inside here to make it ready for plugging these values in. Now, we do know what power a half means. It's the square root. So that's now getting to a form where we can understand plugging numbers in. Square root of 10 minus 3x. On the bottom of this fraction, we have negative 3 times 1 half. So it's negative 3 halves. And square brackets telling us we are about to plug in 2 and plug in negative 5 when everything's ready for that. Now, next, tidying up. Positive expression divided by a negative expression. We'll get negative expression altogether. 3 over 2 on the bottom, we want to get rid of that divide by 2. So we're in a fraction, we can double top and bottom. So we double the top of the fraction, double the root 10 minus 3x, and double the 3 over 2. The 2's disappear and we'll get 3. A couple of 1.5's give us 3. And I'm going to plug in the values 2 and negative 5 when this expression's ready. Well, it is ready now. So we can go ahead with calculating this. Now remember, there's no calculators in paper 1. So it's all fun and games. So in the first bracket we plug in 2, in the second bracket we plug in negative 5, and it's a difference. So let's put that 2 in. So it's square root of 10 minus 3 2's divided by 3. And let's plug in the negative 5. So it's negative 2 lots of square root of 10 minus 3 lots of negative 5. And that's divided by 3. So we're making progress. We've done the substitution. And let's see what happens now. Under the square root sign, we've got 10 minus 3 lots of 2. 10 minus 6 is 4. Square root of 4 is 2. So on the top line, we've got 2 times 2. Well, that's 4. So that's 4/3. Remember, there's a negative at the front. So that's certainly a huge simplification. Here we're taking away a negative number. That's just the same as adding. So that takes care of the two negatives. Under the square root sign, what have we got? We've got 10, and a negative 3 times a negative 5 will be a positive 15. So we've got 10 plus 15 is 25. The square root of 25 is 5. We've got 2 lots of 5. That's 10. And 3 on the bottom. Well, we're almost there. We've basically got 10/3. Take away 4/3. We'll get 6/3. That's 2. Isn't that satisfying? So here we have question 7, where we've got a couple of triangles superimposed in each other, A, B, C, a large one up there, and A, D, E, right angled triangles. We've got Q and R marked in as the size of these, and we've to determine the value of first sine R and then sine Q. So sine R, angle R is in triangle ADE or DAE. So let's first of all look at that diagram. There I've extracted it from the picture. And the sine of R would be the opposite over the hypotenuse. Now we don't know the hypotenuse, but we're in a right angled triangle. This side is 1. This side here is 3. 1 plus the 2. So this side will be the square root of 1 squared plus 3 squared. That's the square root of 10. So this is A part 1, and we can now confidently say that sine of R is 1 over root 10. So let's look at the second triangle, the one that involves Q. There's another right angled triangle, and the sine of Q would be the opposite over the hypotenuse. Now this time we know the hypotenuse, we don't know the opposite. So this is A part 2. And again we'll use Pythagoras' theorem in this triangle to work out the smaller side. So it'll be a difference, square root of the hypotenuse squared, that's root 13 squared, which will be 13, minus 2 squared. So that's 13 minus 4, that's the square root of 9, which comes to 3. So this side is 3, and that immediately allows us to give the value of sine Q as opposite over hypotenuse, 3 over root 13. So that's part A. So let's move on now to part B. And in part B, we're asked to determine the value of sine Q minus R. Now, an expression like sine Q minus R is just crying out for an expansion. It's what's called the difference formula, sum and difference formula. And the pattern for expanding something like this, when it's a sine and a difference in there, is sine cos cos sine. So we have the sine of Q times the cosine of R minus the cosine of Q times the sine of R. Now most of these things we know, at least 2 of them have already worked out. Let's have a look. Sine of Q, there it is, in all its splendour, 3 over root 13. And we're asked to multiply that by cos R. Cos R we don't have, But let's go up to the top triangle, the cosine of r, adjacent over hypotenuse. That'll be 3 over root 10. We have to subtract the cosine of q. Do we have that one? No, we don't. So let's work that out. In the bottom triangle here, cosine of q is adjacent over hypotenuse. That's 2 over root 13. And we have to multiply that by the sine of r, and this we do have. That's 1 over root 10. So we're making good progress here. Multiplying two fractions together, multiply the top numbers, bottom numbers. 3 times 3 is 9. Root 13 times root 10 is root 130. Minus 2 times 1 is 2. Root 13 times root 10 is root 130. Now, same denominator, so we've got 9 of these minus 2 of them. That would be 7 of them. So 7 over root 130. That'd be a perfectly adequate version for the answer. It just says determine the value, and that is the exact value. No calculators in paper 1. So that's the exact value of sine q minus r. So this is question 8. And we're asked to solve this log equation. Got a sum of two logs. Notice they're the same base, so the laws of logs can be moved in there to simplify things. So sum of two logs equals 2. We're told x is greater than 0, and that will become important towards the end of this question. So let's remind ourselves, because we have a log sum, let's remind ourselves of the law of logs that involves the sum of two logs. So here's the sum of logs, and if we're adding the logs of two numbers, we must have been multiplying these two numbers together. So a log of m plus log of n is the log of m times n. So that's one of the laws of logs, and it's the one we'll use here. So log to the base 6 of x plus log to the base 6 of x plus 5 gives us 2. If we're adding two logs, we're multiplying the numbers. So it'll be x times x plus 5. And that gives us 2. So we're now looking at a situation. Let's take an example. Let's say one we understand. Log to the base 10 of 100. What power do you raise 10 to get 100? The answer's 2. And why is that? Because 100 can be written as 10 squared. So this is a log statement. There's the equivalent power statement. It's always worthwhile having a numerical example just to remind you of how things work. I mean, the actual law in terms of letters that we're looking at would be something like this, where the equivalent would be what power do we raise b to get m? The answer is n. So we'll get m by raising b to the power n. Maybe not so easy to remember. This one will be easier to remember. So always compare it with a simple numerical example to help you on the way. But there's the way to read it. What power do we raise 10 to get this number 100? The answer being 2. So this number 100 will be 10 squared. This number x times x plus 5 will be 6 to the power 2. What power do you raise 6 to get this number? The answer's 2. So this number here you can get by raising 6 to the power 2. Now at this stage we're in familiar territory. This is looking suspiciously like a quadratic equation. Let's multiply out the brackets. And then we've got a 36. Let's take that from both sides. And there's a good healthy quadratic equation which hopefully we'll be able to factorise. So let's hope your factorisation skills are up to this. We'll have an x and an x. So we're looking for something times something gives us 36, and the sum or the difference will give us a 5. So 36, 6 times 6, that's not going to be helpful. So let's try 4 times 9. There's another positive. That looks promising. There's a difference of 5 there. Let's attempt that then. So we'll put the 4 and the 9 in. Now this may not be the way you factorise, but it's the way I factorise, but use your own method. Anyway, I'm now looking at first outsides, insides, last. I'm looking at the outside 2 being 9x. Still haven't decided on the pluses and minuses. The inside 2 giving me 4x. And I know looking at this result that these have to combine, adding or subtracting, to give me 5x. So I'd have to have positive 9x, and I'd have to take away 4x from 9x to get positive 5x. So I now know my 9x, that's the outside 2, is positive. There's x times positive 9, and the inside 2 give me negative 4x, so there's negative 4 times x to give me these, to give me the negative 4x. So that's fine. If you want, do your first outsides, insides, last, work backwards just to check that we do get x squared plus 5x minus 36. So that does work. Therefore, what have we got? We've got this expression times this times this gives us 0. One or other of these must be 0. So either x minus 4 is 0 or x plus 9 is 0. If it was the case that x minus 4 was 0, we add 4 to both sides, x is 4. If it was the case that x plus 9 was 0, we take away 9 from both sides. Now, remember what we read out at the beginning. X has to be greater than 0. So we'd better state why we don't want this second solution. However, we're told x is greater than 0, so x equals 4 is the only solution. Now you may want to double check that. If we go back in here, 4 times, putting 4 in this bracket, 4 plus 5, 9. 4 times 9 is 36. So at this stage that would say log to the base 6 of 36 is 2. What power do you raise 6 to get 36? Answer's 2. 36 is 6 squared. So yes, it all ties up. That seems to be the solution. So here's question 9. It's a trig equation. We have on the left hand side cosine 2x. On the right hand side we have 5 cos x minus 3. Now looking at cos 2x should bring to mind the double angle formula. At the beginning of your exam paper you'll have recourse to the formula sheet, and on that formula sheet you have the 3 versions of cos double an angle. Now looking at the surrounding scenery here, we see cosine x. We don't see any sine x's at all. So the versions we're going to use, we don't use this, we don't use that. The version we're going to use would be the one that only involves cosine. There's no point in introducing sines when they're not there to begin with. So the left hand side we can replace by 2 cos squared x minus 1. And the right hand side is 5 cos x minus 3. Now, a more familiar setup that involves things like that, suppose it was just x was the unknown and not cos x. If you're faced with this type of equation, you immediately recognise that as a quadratic, and you would move everything onto the left hand side to make it equal to 0 and maybe factorise or use the quadratic formula thereafter. So let's tackle this by doing exactly the same. We'll leave the squared term where it is. We'll subtract 5 cos x from both sides. So that'll disappear. And we'll add 3 to both sides. 3 onto -1 will be 2. And we've got rid of everything on the right hand side, so we get a 0 there. So yes, we're at the stage where we have something like 2x squared minus 5x plus 2 equals 0, and we'd go ahead and attempt to factorise that expression. So let's do that. Let's put our 2 brackets down. There's all sorts of ways you might have been taught how to factorise. I usually use the first outsides inside last method, working backwards. So I know that the 2 firsts are giving me 2 cos squared x. So let's try a 2 cos x times a cos x. It has to be that. And the lasts give me 2. So there's 2 ways of doing this. I could put a 2 in here and a 1 in there, 2 times 1. You see, the outsides would then be 2 cos x and 2 cos x. It's not much use to try and get a 5 out of that. So the other way round, doing a 1 and a 2, would give me the outside terms multiplying. I would get 4 cos x when I multiply these. And the inside 2, I haven't worked out the pluses and minuses yet. I'll do that in a minute. 1 times the cos x gives me 1 cos x. And if I'm attempting to get a negative 5 cos x from these 2, I would take -4 and another -1. So both terms would have to be negative. And we just check that the lasts do tie up with the +2. -1 times -2 does give me that +2. So remember, always check first outsides, insides, last. When you think you've factorised it, multiply it out, see that you do get the expression you were trying to factorise. So this does make sense, it works. We've got 2 factors, this times this gives me 0, so one of other of these factors must be 0. So either 2 cos x minus 1 is equal to 0, or cos x minus 2 is equal to 0. Now if it was the case that 2 cos x minus 1 is 0, add 1 to both sides and then divide by 2, you'll get cos x being positive 1/2. If this was the case, then add 2 to both sides, cos x equals 2. Now let's deal with this second equation first. We're hunting for an angle whose cosine is 2. Now, recall the cosine graph. Here is the cosine graph. We're hunting for an angle along here whose value of the cosine would be more than 1. Now you can see that the biggest value the cosine ever takes is 1. Cosine of 0 is 1. It then gets less and goes all the way down to -1, back up to 0 and back up to 1. Cosine of 360 degrees is 1. And it continues on that wonderful graph where it never ever goes larger than a value of 1. So if you're hunting along here for an angle whose cosine gives you an answer bigger than 1, you'll be there forever wandering along there searching for it. There is no solution. So for cos x equals 2, there is no solution. And if you want more details than that, you can put out in its gory details that cosine values of the cosine always lie between -1 and 1. So that's that second possibility dealt with. And if we look at the first equation for cosine of x being 1/2, then we can immediately tell that the angle is in, well, there's an angle there, first quadrant or along here, that's the fourth quadrant. You might well use this diagram, and you'll be saying that the cosine is positive. That happens in the first quadrant, angles between 0 and 90, where the sine, the cosine, the tangent, they're all positive, or the fourth quadrant where only the cosine is positive. That's there. So the angle x is in first or fourth quadrant. So we now determine what the first quadrant angle is. This exact value in paper 1, you don't have recourse to your calculators. We're dealing with 1s and 2s for a cosine. That would involve an equilateral triangle. So we use an equilateral triangle of side 2 and we chop it in half. This side is half, so we get a 1. Pythagoras, 2 squared minus 1 squared, square rooted, that's square root of 3 for the third side. That's your 60-degree angle. Up here is half of a 60-degree angle. So this little diagram will help you with the sines and cosines and tangents of the exact values of 30 and 60 degrees, sine, cos, tan of these. And so we're looking at the cosine being a half. Now let's attempt cosine of 60 adjacent over hypotenuse. That's bang on. That's 1/2. Cosine of 60 is 1/2. So the angle x is 60. And you can see that in this diagram. If we go along here, there's 60 degrees. Now there is another angle. And by symmetry, you can see you've got 360 minus that 60 degrees. We'll have 300 in there. If you're using this diagram, you start off with 60 in the first quadrant. Your fourth quadrant angle, you go all the way around to 360 and subtract the 60. So it's 360 minus. So 360 minus 60, which is 300. So solve that equation. We're okay, we're within the range 0 up to 360. So solutions are 60 and 300. Two of them, first and fourth quadrant angles. So here's question 10. We're showing the graph of a cubic function, y equals f of x. We're told the curve has stationary points at 0, 3. It's a maximum stationary point. And at 4, 0, there's a minimum stationary point there. First of all, we're asked in part A to sketch the graph of y equals twice f of x plus 1 using the diagram provided. So to get a feel for what's going on here, I think we should do some explorations. Well, here we're looking at this red graph of the function y equals f of x, very similar to the graph in the question. We're now going to look at the effect of changing this number at the front of the graph. At present it's 1, y equals 1 lot of f of x. In other words, y equals f of x. And we're going to change this value. Let's increase it. So we're now looking at, for instance, y equals 1.3 times f of x. That's the red graph. The original y equals f of x graph is shown in blue dotted line. So let's increase this up to a equals 2. And you'll notice that the height for a particular value of x, say x equals 0, the height on the original graph y equals f of x was 3. The height on y equals 2f of x, 2 lots of f of x, has now been doubled and it's 6. All the heights on the old graph, there's a height of 1.5, have been doubled. It's now 3. And obviously heights of 0, when you double a height of 0, you still get a height of 0. So where the graph, the original graph, that's the dotted blue graph was touching the x-axis, it's still, the red graph is still touching the x-axis. Same here. So all heights have been doubled. And we can keep going with this. Another way of describing this is that the old graph has been scaled along the y-axis, in the direction of the y-axis, in this case by a scale factor of 2. Of course, if we go down and multiply the original f of x by 1/2, you can see where the heights used to be 3, they're now half of that, 1.5. And again, the heights, if they were on the x-axis, height of 0, they're still a height of 0. So a scaling this time, scale factor 1/2, a sort of squashing of the original graph along the y-axis. So that's the effect of multiplying f of x by different numbers. Scales the graph in the y-axis direction. Let's look at this one where we're adding a number to f of x. Let's increase that value to 1. So we're now looking, red graph is y equals f of x plus 1. And you'll notice where we had a height of 3 in the original y equals f of x graph, the height has had 1 added to it, 4. Where the height was 2, it's now 3. Where the height is 0, it's now 1. So the whole graph has been translated by a factor of 1 unit parallel to the y-axis. All heights have had 1 added to them. So there's a height there of -3, it goes up to -2. So that's the effect of adding a constant at the end. Now, the question asks us about the graph when we double and add 1. And here is that graph where you can see the heights have been doubled and 1 added. This height of 2 went up to 4 with 1 added. A height of 0 doubled still gives you 0, but 1 was added. So that's the resulting graph. Now it certainly doesn't stay on the x-axis where it used to. This point here, height doubled is 0, but we had to add 1 to that. So let's get back to the question and sketch in the answer. So here we are back at the question, and let's have a look at this answer grid where we're x and y axis. I've sketched in dotted line the original graph, so we know this is a height of 3. And then the first thing we're doing is doubling all the heights. So height of 6, height of 0 still remains as 0, as does this one. And this height gets doubled. This height gets doubled. So we can begin to see the shape there. And this height goes down to there. So let me attempt to sketch in the doubled 2f of x. So that's that. Now, finally, we have to add 1. So this will go up to that point. This will go up 1 unit. This will go up 1 unit. And all the points in between will go up by 1 unit. And in particular, this one here will go up 1 unit. So let's draw that in as best I can. So long as we're above that doubled graph, there we go. So that's the best I can do with the facilities I've got. This point, we need to annotate the graph, would be 0, 7, the point where it crosses the y-axis. We know that. We've doubled that height and added 1. Similarly, this now, the minimum there, would be 4, 1. So there's the annotation that we know of. These were the 2 points that we knew on the graph. And we must show where they end up. So this is the graph y equals 2 lots of f of x plus 1. We'll put the label on that graph. So that's that. And let's think about part B, where they ask you to state the coordinates of the stationary points on the graph of y equals f of a half x. Well, again, let's do some exploration to find the answer to that. So here we are back at the demonstration, where we know multiplying by this number scaled the graph in the y-axis direction, and adding a number at the end translated the graph parallel to the y-axis. And our final part, B of the question, is asking us what effect multiplying the x inside the formula or the function, what effect does that have on the graph? So let's try and double x first of all and see what happens. Now you have a look and see what's happening. So the dotted line shows you the original y equals f of x. We're now looking at y equals 2x. Let's do that again. We'll go back to y equals f of 1x, and we're increasing the value that we're multiplying x by until we reach y equals 2x. Now, I think you can see that what's happened is we've done a scaling of the graph by a scale factor of 1/2 parallel to the x-axis. The way we should be thinking about this is where the behaviour of the graph at 4, since we're now doubling 2 to get 4, we're doubling the x value. So where we now have a 2 going into the graph, it'll behave like it used to when x was 4. To double 2 gives you 4. So at this point it's behaving like the old graph did. And that will continue. We get a scale factor of 3 along parallel to the x-axis, squashing the graph up in that way. Now let's go back down y equals f of x again. So now the question asks us what happens when we get f of half of x. Now you may have imagined what goes on if we're multiplying by 2 and we have a scaling of a half, squashing of the graph. Maybe when we half x, we'll be scaling by 2. Let's check it. There we go. It's stretching the graph out, scaling the graph, and when we reach a half x, we have scaled the graph along the x-axis by a factor of 2. So now when x is 8, because we're multiplying this x value by a half, where we've got an 8 going in place of x, a half of 8 is 4, so we've got f of 4. So the graph out here, new graph, is behaving like the old graph behaved at half its value. So scaling out, factor of 2 parallel to the x-axis. And so it goes on. There's even stretching it out further. So scaling by halves and thirds and so on, and then scaling by times 2, by times 3 and so on. So let's go back to the question and see if we can finally answer part B. So multiplying x inside the function by a half will scale this graph by a factor of 2 parallel to the x-axis. Now that means that this stationary point will remain where it is. All the points on the graph will move out, but this point will remain where it is. So state the coordinates of the stationary points. This is part A up here, and part B, the stationary points on that graph. Stationary points are 0, 3 as before, and well, this is the point that will move out by a factor of 2 from the origin, so it will become 8, 0. So remember, what goes on when x is 8, when 8 goes in there, you get half of 8 is 4. It then behaves as on the original graph when x was 4. So when x is 8 on the new graph, there will be a minimum point because there was one at 4 on the original graph. So here we have question 11. It's a quadratic expression, 2x squared plus 12x plus 23. And we're asked to express it in a certain form, which is a squared. It's called completing the square question, this one. But we notice that we've got an x plus q times an x plus q, two terms that are identical. And x times x gives us an x squared, not a 2x squared. One of the ways that we can tackle this is to get rid of that 2 as a common factor. Now the number at the end we can sort out later, but basically at the heart of this we've got a x squared plus 6x. X squared plus 6x. And if we have to write this as two terms that are identical, with an x and an x, and you notice that the outside two terms and the inside two terms, that's your FOIL, your firsts, outsides, insides, last, these outside and inside terms will be identical. Why? Because this is a squared term. These two brackets are identical. X plus q squared. They're identical terms. So they must both be equal. So many x, same number of x, and we have to get a 6x, so there'll be 3. 3x and a 3x. So we know in the process of working this out, we're going to have to get an x plus 3 times an x plus 3. But there's a 2 to involve us with and a 23 at the end, so it's not straightforward. Let's multiply out x plus 3 times x plus 3 and see what we get. So the first give us x squared. Outside and insides are both 3x, that gives us a 6x. However, there's a plus 9 appears. Now this 2 that's outside doubles all of this, so 2 lots of x plus 3 all squared will be 2 lots of this expression, 2x squared plus 12x plus 18. So we're not there yet. 2 lots of x plus 3 all squared, this is not equal to that, because it's 2x squared plus 12x plus 18, and yet this has a plus 23 there. Well, how can we change a plus 18 into a plus 23? I suppose that'll be adding 5. So here we are with 2 lots of x plus 3 all squared plus 5. Now, if you don't believe that we've done this correctly, then you would have to multiply the thing out just to double check that everything is as it should be. So we'll have two lots of x squared plus 6x plus 9 plus a 5. And that gives us 2x squared plus 12x plus 18 plus 5. And that 18 plus 5 gives us the 23 that we wanted. So we end up with the expression that we started. So that was the clue. Get rid of that 2 out as a common factor in the first two terms and concentrate on that x squared plus 6x. And because it's a squared expression, each of them must be x plus 3. You notice the 3 is half of that 6. That's the heart of this problem and solving it. And everything else, we just mould it so that the thing fits in. So 2 lots of x plus 3 all squared plus 5. And that's in the form that we were asked to write it. So here's question 12. It's a differentiation question. F dashed is to be found. We have to differentiate this function f of x to get f dashed, and then we have to plug in a value for x to find out the value, evaluate it eventually. So our first task then is to differentiate the function f that we're given, and it's 4 times the sine of an angle. Now the formula for differentiating sine is straightforward. You differentiate sine x, you get cos x. Now, that would be fine, however it's not an x that we're involved with for the angle. So differentiating this, and remember if a number appears at the front, it just still appears at the front in your answer. So if this was 4 sine x, we would get 4 cos x as the answer. However, it's not x, it's a linear expression, another expression, 3x minus pi upon 3, and the chain rule comes into action where we have to make an adjustment by differentiating the thing that's pretending to be an x. So if we differentiate 3x minus pi upon 3, that constant disappears and we end up with 3. That's the coefficient of x that we're multiplying. So there's an adjustment to be made because it's not 4 sine x. It's a more complicated expression. We have to differentiate that expression to get 3. That's the adjustment we make by multiplying by it. So we end up with 12, 3 lots of 4 cos 3x minus pi upon 3. So that's us with our f dashed of x formula. So we now have to plug in a value for x. It's pi upon 6. So we just take this expression and replace x by its value, pi upon 6. And let's work away at that angle for a wee minute and see what we have. 3 lots of pi upon 6. We divide top and bottom by 3. We'll get pi upon 2. Now for subtracting fractions of pi, halves and thirds, well, let's change them into sixths. So multiply that by 3, multiply that by 3. 3 lots of pi upon 6. Let's multiply top and bottom here by 2. So that's 2 pi upon 6. So what we're faced with in this angle is 3 lots of pi upon 6 minus 2 lots of pi upon 6 That would be one lot of pi upon 6. Just pi upon 6. Now, no calculator in paper 1. Can we work out the cosine of pi upon 6? Or 30 degrees? Yes, we can. A 30-degree angle is going to occur if we use an equilateral triangle. All sides are the same. We'll say their side 2, chop that in half. There's 1, 1, 2, and root 3 by Pythagoras. This angle 60, it's pi upon 3 radians, and this angle up here is pi upon 6, it's 30 degrees. So we're asked to find the exact value of cos pi upon 6. We're up here. Cosine is adjacent over hypotenuse. That's root 3 over 2. So it's 12 times root 3 over 2. And cancelling top and bottom by 2, we'll get 6 lots of root 3 over 1. So that's just 6 lots of root 3. And that's the exact value of f dashed pi upon 6. So here's question 13. Part A asks us to show that x plus 2 is a factor of this cubic polynomial, which they're calling f of x, and therefore we have to solve the equation f of x equals 0. So let's first of all have a look at showing something as a factor of something. Suppose we divide 9 by 2. We know it goes 4 times and there's a remainder of 1. That means that 2 is not a factor of 9. In fact, what we've shown is that 9 is 2 times 4 and there's a remainder of 1. We'll have to add 1 to that. So 2 is not a factor of 9. If we're asked to show that 2 is a factor of 8, however, 2 into 8 goes 4 times and the remainder is 0. And we've shown that 8 is 2 times 4 and hence 2 is a factor of 8. Divides into 8 exactly. So if we're asked to show that x plus 2 is a factor of this cubic, we'd have to divide x plus 2 into this cubic and show that the remainder was 0. And that's what's called the synthetic division scheme. So we set up a division. The code for x plus 2, if you like, is the value of x that makes this 0. X would be negative 2 in that case. So we set up a negative 2. There's our division scheme. Now the code for this polynomial are its coefficients. So there's 1x cubed, there's negative 2x squared, there's negative 20x's, and there's a constant of negative 24 at the end. Had there been missing terms, like no x squared term, we still would have had to have put a coefficient of 0 in there. So that's the setup. We do the division. Now you'll have learnt this routine. We bring the 1 down, we multiply by negative 2, we add these two, we multiply again by the negative 2, that gives us positive 8, we add, we multiply by the negative 2, and then we add again. And just as this example was a 8 divided by 2 going exactly 4 times remainder of 0, x plus 2 into this polynomial goes this number of times, we'll come to that in a minute, with a remainder of 0. So what we can say about this is, since, and we have to state this, since the remainder, you have to show that you know what this 0 means. Since the remainder is 0, then x plus 2 is a factor. It's like the conclusion of this. Since the remainder is 0, 2 is a factor of 8. And just like we were able to write 8 as 2 times 4. We're going to do the same here. This polynomial up here that they're calling f of x, and this is part 2 we're on to. There's part 1. We're on to part 2. This polynomial f of x, since we've divided it by x plus 2, it becomes x plus 2 times, and that's the number of times it goes in to this polynomial. Just like 8, 2 into 8 goes 4, so 8 there can be written as 2 times 4. This polynomial can be written as x plus 2 times this polynomial. Now that polynomial that's sitting down there, that's coded. It's the coefficients we're given. So it's 1x squared minus 4x minus 12. You see there's just 3 of them. So it's a quadratic. X squared, x, and a constant. We started out with a cubic. There's 4 terms there. And we end up with a quadratic. So that's what f of x is equal to, in the same way that we wrote 8 as 2 times 4 there. The remainder is 0 when we divided this by x plus 2, and it goes x squared minus 4x minus 12 times. So, what does that mean? It means if we're trying to solve this equation f of x equals 0, then we know the equation can be written as x plus 2 times the quadratic x squared minus 4x minus 12, and that's a product that we're wanting to equal to 0. So 2 things equal 0. We know this could be 0 or this could be 0. Now one way of solving a quadratic equals 0 is to factorise it. So we've still got a wee bit of factorising to do. So let's put our 2 brackets down and see if this factorises. So the first terms would be x and x. Factors of 12, 2 times 6, that'll end up with a possibility of getting a negative 4 there. So it would be minus the 6x plus the 2x. You'll have your own way of factorising something like that. You use the way you're used to. So these 3 expressions multiplied together give me 0. Somewhere along the line there must be a 0. So either x plus 2 is 0 or x plus 2 is 0. That gives us the same as the first equation, or x minus 6 equals 0. So what do we get? If x plus 2 was 0, x would be negative 2. Now you'll notice that's the same as the second one. We sometimes call that a repeated root. And if you're looking at graph, how that's interpreted on a graph, usually the graph just touches the x-axis at the point where x equals negative 2. So that's a repeated root, or x equals 6. So we have solved the equation and got these 2 roots. So let's move on to part B of this question. A lot of new information given. We're actually shown the graph of this function. There it is, y equals f of x. And as we said, the repeated root x equals negative 2. Remember the roots, when you set the values of this function equal to 0, you're talking about where are the heights on the graph. 0, that's there and there. So repeated root, remember I said it was where the graph would touch the x-axis. So we're talking about a negative 2 there, and that's our 6. So that's the typical cubic graph, and that's where it touches or crosses the x-axis. So we've identified the 2 roots in that. So there's the graph of y equals f of x. Now they're asking us, or they're telling us that a different graph, the graph of y equals f of x minus, and they're subtracting a number from x inside the bracket, and we're told it's a positive number they're subtracting, and it has a stationary point at 1, 0, and we have to state the value of k. Well, let's go and explore the effects of subtracting a number inside the bracket. How does that affect the graph of a function. Let's explore that first. So here we have the graph shown in the question, and we're going to be looking at the graph not of y equals f of x, but f of x minus a constant h. Now at present I've set that constant to 0, so we are in fact looking at the graph y equals f of x. So let's see what happens when we start subtracting numbers from that. Let's subtract 1. And you'll notice that there's the old y equals f of x graph shown in blue and dotted line. And we'll notice that the graph has moved 1 unit to the right. So that what's happening now when x is -1, if we put x equals -1, we've got -1 minus another 1, that's at -2. So it's behaving at -1 like it used to behave at -2, because when we put -1 into this function, we get f of -2. And similarly, if we move to an h value being 2x minus 2, let's move 2 units to the right. 3 units, 4 units, and so on. So when we subtract positive numbers from x, then the graph moves to the right. Now, this is not required for the question, but if we subtract negative numbers, in other words, add numbers, that would be adding 1, that's f of x plus 1, it moves 1 unit to the left, 2 units to the left, and so on. So when we add numbers, taking away negative values, that's adding positive numbers, then it moves to the left. But for the sake of this question, if we're taking away 1, it moves 1 to the right. If we take away 2, it moves 2 to the right, and so on. So let's keep that in mind as we now look at the question they're asking us to solve. So here's what they're telling us. They're telling us that if we subtract a number from x in this formula f of x, then the graph we get is a stationary point at 1, 0. Now remember, the effect of taking away positive numbers, taking away 1 moves it 1 to the right, taking away 2 moves it 2 to the right, taking away 3 will move it 3 units to the right. And they're telling us there's a stationary point at 1, 0. So there's a stationary point, and if we move that stationary point 3 units to the right, then k will have a value of 3, and that would fit what they tell us. So and we're saying shifting the graph y equals f of x 3 units to the right means k equals 3. Giving a stationary point at 1, 0. Stationary point used to be at -2, 0, moving the graph 3 units to the right. The stationary point's now at 1, 0. And the effect of x minus 3 would be moving y equals f of x to the right by 3 units. So k equals 3. So here we have question 14. We're given the equation of a circle called C1, and we're asked to state its centre and radius, and we're asked to show that this particular point P, of which we're given the coordinates, lies outside C1. Now the crucial fact for part A here is finding the centre and radius, and we refer to the standard equation which is given in your formula sheet in the exam. There it is, x minus a all squared plus y minus b all squared equals r squared. That's the equation of a circle which has centre AB and radius r. So we'll use that to solve the first part. So the centre, and let's call it C. We compare this with this. We can see that A is 7 and B will be -5 to get that +5 there. So 7, -5 is the centre. And the radius, well, this is number that appears here is r squared, the radius squared. So 10 squared gives you 100. So the radius is 10. It's the square root of that, 100. So that's the centre and the radius. Now part 2 asks us to show that that point P lies outside C1. Let's have a look at a diagram first of all. So let's get a pair of axes, the x and y axis. Centre is 7, -5. So that's the centre C, 7, -5. And the radius is 10. So let's just estimate this. That looks okay for where the circumference is going to lie. So, doing my best to create a circle. So that's roughly what the circle looks like. So the point -2, 7, up here somewhere, -2, 7. And we're asked to show that this point lies outside that circle. Well, I think what we should maybe do is look at the distance from P to C. So that's the first thing we'll do. So from P to C, and distance formula is used, square root of the x difference squared plus the y difference squared. X difference would be, say, 7 minus -2. That's 7 plus 2. And the y difference, -5 minus 7. So that's 9 squared, that's 81. And that's -12 squared, 144. And that'll give us a square root of 225, which is 15. So distance from P, point P, to the centre of the circle C1, that's circle C1, is 15 units. Now, what is the radius of this circle? We found out it was 10. So certainly, if we join up these 2 points, then there's a radius, which is 10, and therefore P has to lie outside the circle because the distance between P and the centre is greater than 10. So we can say that PC is greater than the radius, which we know is 10. So P lies outside the circle. So that's that. Now let's have a look at part B. We're told that C2 is a circle with centre P and radius R, so they're not telling us precisely what the radius is, that it's just R. So it's that circle, radius R, and we've got the original circle. So this is C2. And we have to determine the values of R, that's the radius of this, for which circles C1 and C2 have exactly 1 point of intersection. Now, I don't know how good your imagination is, but I'm seeing a picture of this circle expanding gradually until it touches this circle. Let's have a look at that. So here we have the situation where up here we've got a circle, it's a very small circle just now, around the point -2, 7, and that's our fixed circle C1. Now let's increase the size of that circle. The radius is now 1, it's 2. You can see what's going to happen. When the radius is 5, the two circles touch. Now how do we know it's 5 for that radius? Because the radius of C1 is 10, and we know already, we've calculated that the distance between the two centres is 15. So along this line joining the two centres, we have to have a distance of 15. So a radius of 5 plus the radius of 10 gives me that 15 distance. So let's, however, not just satisfy ourselves that that's the answer, because with a bit of imagination we can find another position for that circle where it just touches the other circle. So far there's 2 points of intersection. You can see them there and there. But as we continue increasing the radius, there comes a point where it touches the other circle, and that's just before it completely misses the circle. So at that position there, and the slider here says 25 by the looks of it, well, let's just check if that is 25. So we have that distance of 5 plus that distance of 10 plus another distance of 10. You see the diameter of this circle C1 is 20 plus that 5. You get 25 for the radius. And again, we know that the distance from this point to this point is 5 plus 10. So 25 is also another value for the radius. So 25 and 5. So that's two values for the radius of this circle where it just touches circle C1. So I think what we do then, finally, is we just write the two values down. So R equals 5 or R equals 25. So this one gives you an external touching, and the other one gives you what's called an internal touching. So we had in this case a very large circle with C1 touching inside, and in this case we had a small circle with a larger C1 outside it. That's Mr. Corsi signing out. Hope you enjoyed the video.